Continuing with Newton's laws, and more specifically, Newton's third law. Newton's third law deals with the third law pairs, and that is your action-reaction pairs. So whenever one object exerts a force on another object, the other one exerts the equal and opposite. It's why when you would, if you ever go hunting, that you need to snuggle up to the firearm, because the reaction of the bullet leaving the muzzle is the butt of the firearm coming back into your shoulder. And you want to increase the amount of time that is. You are able to walk because of Newton's third law. Without Newton's third law, you can't walk. The force that you put into the ground is the force that allows the ground allows you to propel forward. Equal and opposite. Hitting your hand on a desk. And I love this picture because, man, would that hurt. It's like, ouch! But just remember, no matter how hard you hit it, it hits you back just as hard. Because Newton's third law. So now when we look at doing our free body diagrams, we do need to identify our third law pairs. Okay? And remember, sometimes there are what we call Newton's first law pairs, such as weight and normal. Okay? On a book sitting on a table that's not moving is going to have a Newton's first law pair. The weight of the book goes down, the normal force of the table pushing on the book is up. Those are not equal and opposite. What you then would need to do is do a Newton free body diagram for the table and see that the table pushing on the book and then the book pushing on the table. Okay? Equal and opposite.
Doesn't the third law...
So, again, and Newton's third law is one of the two that most people know. Most people know the first one. Okay? It's usually the get out of bed law. An object at rest will stay at rest until acted upon by an external force. And for every action, there's an equal and opposite reaction. And these are the two. Newton's second law is the one that we utilize the most, but it's not as easy to remember. But it does give us the equation in which we then apply Newton's first law 2, Newton's third law 2, and so on and so forth. And as it says, identifying the pairs, and that is more easily done if we look at, say, when you have a normal force of a table on the book, an equal and opposite of that would be the normal force of the book on the table. And this is where we can see where are we getting these equal and opposites? Kind of the same thing, one's acting on another with this. and it's the same force acting on it. Still a normal force. Tension forces tend to be the same. Weight, there isn't going to be a Newton's third law with weight. There is, it's just because the Earth is so much more massive, we tend to think of it it's minuscule. But the weight, force, Earth on gravity, you technically put a force on the Earth. It's just small, comparable. Collisions are always the fun one to think about, and that's because if the red car pushes on the blue object or the object of whatever it was easy to draw. They say with the same and equal and opposite. Now again, sometimes we always say, but who has the worst day? There's the bug. You know, bug hits your windshield. Bug has the worst day, but there's other things that involve with that. There's a thing called momentum that ultimately really messes things up. Momentum will add another component that's probably where we will end the year at some point, around momentum. That is a picture that did not go through. Because what is supposed to happen is that, and then the red should be opposite here. If I could draw it out a little better, we might have an actual good drawing. Not terrible, but obviously the peaks aren't perfect. But those two lines should be completely mirror images of each other, ultimately. Is what they look like, is what it would look like of a force over time kind of graph. It does bother me. But my abilities to draw the same exact thing are a little lacking, I guess. Oh well. But that's what we would see, is that it should be equal, opposite. One's showing one thing, they're coming in contact, hitting each other. It's usually always kind of one of those ones where, you know, giving a little body check in hockey or in basketball is just that, and you can just talk a little bit of trash maybe. Newton's third law, just keep, and they kind of do that. Just doesn't matter, no matter how hard you hit, you hit me, I'm hitting you back just as hard. Newton's third law. Or, you know, since with those would be some of the things. So, why is it nice? And it's the notation that we get. It is the equal and opposite, subscripting the foot on the ground and the ground on the foot, or the person foot. Again, without Newton's third law, very difficult to walk. We also need friction, so there's always that. You need friction for a lot of these actions and reactions to occur. This is why you can walk on ice, but you decrease your coefficient of friction too much. You slip on ice. You need enough friction to allow you to exert a horizontal force if that decreases increases too much, well, we've all experienced that once or twice. So I've hinted at this a number of times. Bug splats on the windshield of a car moving 100 miles an hour. I don't know where they're driving that legally. Which feels the greater force? The car or the bug?